Okay, so hello everyone. So I'm Tomoaki Ohtsuki from Keio University, Japan. So first, I want to congratulate 30th anniversary of the chapter section. I'm very happy to give a talk about my topic. So today I will talk about AI-based smart healthcare. Okay. Okay, so let's see about the healthcare. Of course, the healthcare is important for everyone, uh, particularly, for example, the people, elderly people, also the people have some health issues. There are various aspects in healthcare, like anomaly detection, such kind of the monitoring, sleep monitoring, and stress monitoring. Anomaly detection, for example, like a fall detection, when people live alone, we want to detect those kind of the very serious issues. Then anomaly detection is important. Also, the sleep monitoring to monitor the sleep state is important one. And also the stress monitoring during the office work and studying at the school or also in daily life. Activity or anomaly detection is mainly, for example, the activity recognition, but sleep monitoring, stress monitoring, and others, or I can say even anomaly detection, vital sign is a very important information. Vital sign, such as respiration, heart rate, blood pressure, and so on. So based on this vital sign or vital information, we can estimate the condition or state of the person. So I can say, or we can say, it is very essential to realize the healthcare. I mean, the vital sign detection is a very essential one. So when we talk about particularly the stress monitoring, we focus on heart rate variability, HRV. What is HRV? Heart rate is always changing due to physical and physiological stress. And it is known that the heart rate is controlled by the autonomic nervous system and many different hormones. So heart rate variability is often measured by this RRI. RRI represents a RR interval. This is a waveform of the heart rate measured by ECG, electrocardiogram. So as shown in this figure, there are several peaks like a P, Q, R, S, T, and the interval between the adjacent R, the largest peak, is named the RRI. So the variation of this RRI, we can estimate the stress condition of the person. Usually we apply the power spectral analysis to evaluate the heart rate variability. So the heart rate variability is decomposed into two components, high frequency component from 0.15 Hz to 0.40 Hz, and low frequency component from 0.04 to 0.15 Hz. So in general, high frequency components correspond to the wave of breathing variation, and it can reflect the parasympathetic nervous system activity. About the low frequency component, this one, it corresponds to the wave of the blood pressure variation, and it can reflect the modulation of the sympathetic and the parasympathetic nervous system. Let's see how HRV changes over 24 hours. These figures show the change of the heart rate variability related features. Left top one is RRI, from noontime, midnight, and the next day noontime. This one, variance of RRI. This one, low frequency components and high frequency component. Let's see the RRI. So, as you can see, from here to here, RRI takes larger value. So that means during the people sleeping, the RRI becomes higher or larger, and the variance becomes relatively large. And related to this one, low frequency component becomes smaller, and high frequency component becomes larger. Okay, so then how to measure the RRI? There are several techniques like this, like the ECG, PPG, SCG, camera, radar, of course some others. So PPG, so this is the Apple Watch. So Apple Watch has PPG, also the ECG, and of course this is a wearable devices, and yeah, if your state is stable, we can expect a relatively high accuracy. But of course, need to attach devices. Yeah, camera, some kind of camera, so we can detect the RRI, like RPP through RPPG. And yeah, we can expect a high accuracy, and also the no need to attach devices. In those sense, it would. But of course, we have to worry about the privacy. If we install a camera inside the house, that means we always monitored by the camera, so it's not so comfortable. And also the performance degrade due to level of brightness. Radar is another technique to detect the vital sign or RRI. And the radar, like camera, no need to attach devices. So in such a sense, user-friendly. However, radar, we always try to detect the very small movement, such as the small chest movement due to heart activity. Then it it can be easily contaminated by noise, such as some body movement. So that's a very challenging part. Okay, so let's see the radar. So radar, this one is a Doppler radar. And as I mentioned, so if we use the radar to detect the chest vibration or chest movement, of course, it can detect the non-contact wave, and also the microwave, so it penetrates to clothing, so no need to require subject to take off the clothing. And of course, the robustness, it's robust to the level of brightness and also the temperature. This is the example of the Doppler spectrogram. So the applying the STFT to the signal obtained by Doppler radar, CW radar, continuous wave radar. The horizontal axis is the time, the vertical axis is represented by frequency. And large energy, those correspond to the respiration, breathing. And also you can see white periodical signal. This is due to heartbeat. So this one, so from this, you can see that we can detect heartbeat and also the breathing. Of course, if the signal is clean, like this one, so it is relatively easy. But as I mentioned, it can be easily contaminated by noise, such as body movement. So that's a very challenging part. the history of the vital sign detection using radar is long. For example, this one, invasive microwave measurement of respiration is published in 1975. So this one, not for person, but for animal. The figure seems to be, I mean, a cat, but according to this caption, so this is the respiratory movement of the rabbit. And also the microwaves penetrate some, I mean, objects. So then these papers, for example, the measurement of heart and breathing signals of human subjects through areas in with microwave life detection systems. So like this one, so using the radar, we can detect the person, also the whether he's breathing or not, we can detect that he's alive or not. So life detection system. There are many techniques to detect the heartbeat or also the respiration by using traditional signal processing technique, like heart rate estimation, FFT, wavelet transform, music algorithm, DCT, and so on. And also, if we focus on the RRI, in addition to this technique, such as the template matching and also the feature detection exist. Of course, the signal quality is good. Then even a very simple or traditional technique can detect the heart rate and respiration. However, particularly the signal to noise ratio is low, and also it is contaminated by noise, so it's not so easy to detect by using only this traditional technique. Okay, so this is one example of the heartbeat detection based on the spectrogram. So left one is a spectrogram obtained by the CW radar. So when the person hold his breath, so you can the breathing. So you can see some, the energy, periodical energy, and based on this one, so this represented the integrated energy over some frequency band, and this red line represents the integrated energy. And this dotted line represents the timing of the heartbeat. So we estimate by using the ECG, so a kind of the ground truth. You can see that some peaks of the red waveform so correspond to this black dotted line. However, you can see some peaks that do not correspond to the heartbeat. So we need to differentiate. We need to detect the true peaks. That's a very challenging part. So this is one of the techniques to detect the heartbeat from the noisy signal. So already 3 years ago, but I want to introduce this one. So this is, as the title mentioned, so based on the deep learning technique. So like the previous one, so we exploit the spectrum, and then in order to exploit the very powerful power of the deep learning, we segmented this image into several segments, then concatenate and put it in the deep learning to reconstruct the signal and try to detect the accurate peak. So here is a model structure. So I don't go into detail, but this is a kind of the relatively normal one. Like you can see some convolutional LSTM layer and also the batch normalization, free connected layer, and so on. This is one of the example of the our technique. So this background is a ground truth. So the waveform obtained by ECG. And the blue one is the integrated spectra. So integrated energy over the spectrogram. And you can see some peaks. Yeah, here we are focusing on the detection of the R peaks. Some peaks corresponding to the real peak, but some don't. So, however, if we apply and our technique and reconstruct the signal, we can see this kind of the signal. So maybe a bit hard to see, but you can see these large peaks corresponding to more accurately to the ground truth one. So how accurate it is? So this represents the RRI variation over the time. So a bit hard to see, but black solid line represents the RRI variation over time. And this is the ground truth. And we want to detect this black line. And this red line represents the proposed method in the paper. And you can see that not perfect, but in relatively good way, our proposed method can track the ground truth value. So that means the deep learning technique can perform well for this kind of task. And also sometimes we want to reconstruct the waveform itself, not only just the R peaks, but also the waveform itself. So this is one of the paper that we propose for waveform reconstruction. Particularly, we focused on the ECG signal reconstruction via Doppler sensor by using the deep learning model. So again, this is the structure, and this is also the usual one, like a composition layer, pooling layer, and LSTM layer, free connected layer, and so on. Then, applying this technique, we can reconstruct ECG signal from the Doppler signal like this. The black one is the ground truth. So you can see the several peaks, and the red one is the reconstructed ECG signal by our method. So you can see, although some peaks still remain, but you can see some important peaks, can be recovered, so reconstructed. So that means using the deep learning technique, we can reconstruct the ECG signal from the Doppler signal. Then how we use this kind of the waveform information. So one example is the blood pressure estimation. So let's see the blood pressure. Blood pressure is, of course, a very important vital sign. And usually we use this kind of device, right? So this is we call cuff. We attach the cuff to the arm, and then they measure the blood pressure. Of course, it's not so uncomfortable, so also not so easy to measure so often. And also we have the VP estimation method based on the PPG, like the Apple Watch, the sensor. And PPG, so like here, blood volume change, it can be measured by illuminating the skin, like a green light. And the waveform, so attaching the PPG to the fingertip, so then we can get this kind of the waveform. From this, we try to also some other researchers try to estimate the blood pressure. So then this is one of our papers to estimate the blood pressure. Yeah, like the title mentioned, using the PPG or ECG. But also this technique can be applied to the sensed data by the radar. So this is a model structure. So like this one is a well-known unit structure, and here, so you can see GRA and also the domain classifier. GRA is a gradient reversal layer. And then domain classifier, so we apply the domain adversarial training. So this is for suppress the overfitting the training subjects. And sometimes so inter-subject, sometimes intra-subject BP estimation accuracy we want to improve. That's why we apply this kind of technique. I don't go into detail, but you can see more detailed information in the paper. So this is the result. So here, the BP estimation accuracy is shown. SVP, DVP, MVP, these represents the systolic blood pressure, DVP, diastolic blood pressure, and mean blood pressure. MAE is the mean absolute error between the true and estimated BP, and R, this represents the Pearson correlation coefficient between true and estimated BP. So as you can see, for example, MVP, we can achieve the relatively high, Pearson correlation coefficient, even for the intra-subject scenario or inter-subject scenario. That means training and testing, no data leakage for different persons. So this represents the blood pressure time series analysis. So the blood pressure changes over time, of course. Then so the black and red dot represent a true MVP with and without filtering, and blue and green ones. So that there is some gap between the true one and the estimated one, but and also that we need some calculation that some a priori information we can make it small, and also that we can see that the rough trend of the blood pressure variation, our technique can track estimate. So then MAE is like this one, 7.83 mHz, and our correlation becomes 0.5 seconds. And also I want to show the radar-based BP estimation. So using radar, so then as I mentioned, the waveform timing information is very important. That is the BP information as I mentioned before. And then not the same technique, but we propose a different technique and presented this year's ICC. So here, again, we employ the integrated spectrum and also the hidden semi-Markov model to estimate the more accurate timing of the heartbeat. And then apply, for example, the random forest model. So some details, please refer to the paper, but using the well-known data set like this one, So evaluated our performance. So here, so the radar is a CW radar, Doppler radar. And here the results. Again, the DBP and SBP, I show the standard deviation and also the MAE. So compared with the reference 8, filtering and artificial neural network, our technique here achieves better performance in various aspects. Compared with 6, you may think that our technique performs a bit worse, but please see here that this technique, condition here, the holding the breath. So if person breathes, of course the effects of some movement, so the performance degrades. So then we cannot compare fairly between them, and usually the performance becomes largely degraded. And then we move to the other things, so mental illness. So first, I want to explain the metric. Years lived with disability, YLD. So this is a measurement of the burden of disease or disability. So number one is the mental illness. So that is a mental illness is a very serious issue in our society. And also the number of patients in Japan about the mental illness like depression, schizophrenia, and so on is 3.2 million, and dementia 1.62 million. But I think that there are much more than these values. Also, the social cost due to the labor loss or something, the depression, very huge. So 31 billion US dollar, and dementia 145 billion US dollar. Well, I can say much more. So what's the current status of the medical examination of mental illness? So in general, as you can, some of you know that the medical examination is through the conversation between the patient and the psychiatrist. And the diagnosis is based on the standards such as DSM-5 and ICD-10. But still, so medical examination results and severity determination depend on the experience of psychiatrists. So based on the conversation. So depending on the person, sometimes differ. So that's the issue. So we want to have some other technique. So one of the interesting, article, or also that we know that people with depression use the language differently. For example, let's see here. Those with symptoms of depression use significantly more first-person singular pronouns, such as me, myself, and I, and significantly fewer second and third-person pronouns, such as they, them, or she. And also the some other absolutist words, such as always, nothing, or completely. So that means that if we see the use of the language, there is a possibility that we can detect a person's mental illness. So this is the one that also that we developed, the dementia detection with large language models. So here, I'm going to explain the large language model based one. So large language model, so probably, so you are familiar with the ChatGPT, that is a large language model. As mentioned here, so large language model is a probabilistic model of a natural language that can generate probabilities of a series of words based on text corpora in one or multiple languages it was trained on. And also the perplexity, this is a measurement of how well a probability distribution or a probability model predicts a sample. So let's see the example. So the mother is washing those are the previous word context. So based on those words, so the model try to predict the next word. So this one, they predict correctly. This one, so yeah, depending on the picture was state, but the clothes. So this is the word wrongly predicted one. And perplexity is like a loss in machine learning. The more accurate the model is, the lower the perplexity loss is. So how we use this language model and perplexity to detect the dementia. So then, for example, we train the language model using the data like dementia person's data, then we can get the language model fitting well on dementia person or vice versa. Like if we train the non-dementia person or healthy subject, then a language model fitting well on those persons. Then if we put dementia person or healthy person, the data and test, then based on the perplexity, we can judge so this person is dementia or healthy. This is the basic idea. So one of our results, so we presented in this paper an evaluation of information composition in dementia detection based on speech. And then this one is a flowchart, as I mentioned, using the dementia dataset and healthy dataset. We train the language model and then test data. Then we see the perplexity difference and we judge this person is dementia or healthy. So we apply several, investigation like how the grammar contains the information to differentiate the dementia person or healthy person or some others, but I will skip these. And this is one of the performance. So here, this scattered plot represents the perplexity difference for each patient. Blue dot represent the perplexity difference of the dementia patients, and this orange dot represent the perplexity difference of control subjects. Then if we set some threshold, so we can achieve, for example, the accuracy of 80.8%. So this is relatively good performance. And the ROC curve becomes like this. And here, AUC, area under the curve, is like a 0.84. Also, not only speech or text processing, but also based on the image, we developed several techniques to detect dementia. For example, not only directly use a raw image or a video, but we apply the face mesh. Face mesh is like this figure, so consists of the 478 landmarks, and each landmark is defined by coordinate X, Y, Z, and visibility. And then connecting these landmarks by a certain order, we can have this kind of the face mesh. Oh, so this is a kind of the face mesh video we obtained from the dementia patient, like this one. So here is the mouth, eyes, and nose. We can see some movement. So why use face mesh? Because one reason is that eliminate the biases. Yeah, in general, so due to environmental biases, so several papers reported, okay, we achieved a very high, detection accuracy, but some papers already mentioned, so probably due to some environmental biases. But like a lighting or background information. If we apply this kind of the face mesh, we can eliminate the biases. And also the more important thing is that we can protect the privacy. Different from the raw image, so the not much information, the personal information is contained in that one. That's why we apply this. So here is one of the model structure, and we achieved accuracy of 0.78, and the other one we are achieving higher one. So this one is as I mentioned, so show here transformer based one. Okay, so I introduced some AI-based smart healthcare technologies, but other than that, there are many, the techniques also that there are many areas that we can, or AI plays a big role in smart healthcare or in medical area, such as medical imaging analysis, developing the drugs first and reduce cost, and diagnosis, early detection, IBM Watson, Google DeepMind Health are a good example, and assistant to medical staff, healthcare management, and so on. So then, I can say AI is very important in medical area, and if you're interested in, I hope you do something about in this area. And in such a case, it's better to note that signal processing, knowledge is still very important. So not only just AI, but traditional signal processing, you need to know and understand. Okay, so this is the end of my talk. So thank you very much.